Meet Samia, a student of environmental science who recently visited her village after many years. As Samia walked through the familiar streets and reminisced about her childhood, she felt a mix of nostalgia and excitement. However, her heart sank when she arrived at the riverside, the very same place where she used to swim joyously with her cousins during her childhood days. Instead of the crystal-clear waters, Samia was confronted with a sight that shattered her soul. The river, once teeming with life and serving as a lifeline for the villagers, was now plagued by pollution. Determined to find answers, Samia reached out to her friends and discussed her concern with them. One of her friends mentioned a powerful tool called Principal Component Analysis, PCA. However, Samia and her friends realized that some of their classmates were unfamiliar with this tool and its capabilities. Understanding the importance of sharing this newfound knowledge, Samia and her friends made it their mission to educate others who were unaware of PCA's capabilities. In the following video, Samia and her friends will delve into the significance of PCA and how it can be applied to measure water quality.
Hello, I'm Samia. So do you know what PCA is? Principal Component Analysis, PCA, is a widely used statistical technique that can uncover underlying patterns and identify key variables in complex datasets. PCA has the ability to offer helpful insights into the detection and prediction of unidentified pollution sources in the context of surface water contamination. Unknown sources of pollution can have significant impacts on water quality, ecosystem health, and human well-being. Traditional source identification techniques frequently depend on expensive and time-consuming field investigations. To address this challenge, PCA can be a tool for enhancing water quality assessment, guiding pollution control measures, and promoting sustainable water resource management.
Though Samia possessed a basic understanding of PCA, including its definition and applications, however, she desired to deepen her knowledge on the subject. To achieve this, she embarked on reading research papers that focused on PCA's implementation in predicting the source of water pollution. Through studying these papers, she gained valuable insights and expanded her understanding of the topic.
Let's explore a summary of what Samia learned from her extensive reading of those papers. To determine water pollution sources and their contributions using PCA, data preprocessing is necessary to ensure consistency, handle outliers, and address missing values. Normalization techniques can be applied to scale variables appropriately. PCA is then conducted on the preprocessed dataset, transforming the original variables into uncorrelated principal components. PCs with high eigenvalues explain significant data variation, and variables with higher loadings in specific PCs indicate stronger influences on pollution sources. Based on these loadings, potential pollution sources can be identified, with groups of variables sharing similar loadings suggesting common pollution sources. Relevant PCs are selected based on loadings and explained variance to use as independent variables in an MLR model, with pollution sources as dependent variables. Coefficients in the MLR model indicate the contribution of each PC to each pollution source. Finally, a pie chart can be created to represent the contributions of different pollution sources.
In order to gain a better understanding, she decided to personally conduct a PCA. She collected data on the levels of total suspended solids in surface water for rivers in her village to assess the extent of water pollution by identifying the parameters that predominantly contribute to it. The parameters she considered included industrial byproducts, decaying organic matter, bacteria, nitrates, sulfate, clay, silt, pesticides, sand, and more. Through the PCA analysis, she ranked the components based on the amount of variance they accounted for. By examining the rotated component matrix, she was able to determine which components or parameters had the greatest influence within the group. Upon completing the PCA, she discovered that component 1 was primarily influenced by bacteria, nitrates, and silt. Component 2 was mainly driven by clay and sand. Component 3 was dominated by industrial byproducts and decaying organic matter. Lastly, component 4 was primarily influenced by pesticides, with a smaller contribution from silt. And after that, she did a regression analysis to know which components are dominating in suspended solids with how many percentages in her data of polluted surface water. She saw about 60% of water quality is dominated by component 3 factors, where 20% of water quality is dominated by component 2 factors, about 15% of water quality is dominated by component 1 factors, and most less contribution is seen by component 4 factor in water quality with only 5%. Lastly, from this analysis, she saw that industrial byproduct, decaying organic matter is mostly dominating as suspended solids. Bacteria, nitrate, slit, clay, and sand are also making some impacts in water as TDS, where pesticides and a portion of slit have seen the slightest impact TDS in polluted water.
Samia later learned from her friend that other than the source, we should also learn about the water quality of the water body. This can be done in many ways. Water quality can be measured directly using handheld testers, or samples can be collected and tested later in the laboratory. In the laboratory, different types of equipment are used to measure water's physical, chemical, and biological characteristics. Then the derived result is compared to local or international standards of water quality. For this process, various models have been developed for accurate measurement. One of these models is the Water Quality Index, WQI, model, which has gained popularity worldwide for its simplicity and is commonly applied to evaluate both surface water and groundwater. It consists of 4 stages. 1. Selecting the water quality parameters. 2. Generating sub-indices for each parameter. 3. Determining their weighting values. 4. Aggregating the sub-indices to calculate the overall water quality index. After calculating WQI, Samia can compare the results to local standards.
Unfortunately, Samia learned that the water quality of her river is bad, according to the Water Quality Index. Using PCA analysis, she identified the source of this problem. It's a textile industry, nearby the river, that is dumping chemicals, toxins and waste materials every day for the past few years. But now with science on her side, she has all the evidence she needs to protect her childhood treasure. Samia and her villagers urged the local government to take appropriate actions to restore the river and ensure the industry takes cleaner and eco-friendly approaches to manage its waste. All of these have been possible due to the HR ad hoc and ongoing research of many scientists who have built various analytical models to protect the environment. Who knows how many rivers these models can save?